This is a video on solving a Newton's laws and kinematics equation problem. So in our example right now, we'll read the problem. A young child is pulling a toy train that consists of 4 cars with masses m1 equal to 1.85 kilograms, m2 equal to 1.13 kilograms, m3 equal to 2.74 kilograms, and the mass of the final car, car 4, is 1.28 kilograms. The force of car 2 on car 3 is 15 newtons east. If friction is negligible and the train starts from rest, how long will it take the child to pull the train 3 meters? So again, as always, I suggest you read the problem first without doing any work, just to get an idea of what's going on. After that, you can reread it, and you can then solve the problem and extract information from your second reading. So in the second reading, we start off, a child is pulling a toy train that consists of 4 cars with masses. We are given the 4 masses, m1, so we write those down. It's time to organize our information. 1.85 kilograms. m2 is 1.13 kilograms. m3 is 2.74 kilograms. m4 finally is 1.28 kilograms. So we've organized that. Then we continue reading. The force of car 2 on car 3 is 15 newtons each. So we say the force, and it's a vector quantity because we have direction, of 2 on 3 is 15 newtons east. Remember, we put our direction in square brackets. And it tells us that if friction is negligible, so we could include that if we want. That tells us the force of friction anywhere is 0 newtons, or doesn't exist. And the train starts from rest, so we know the initial speed of the train is 0 meters per second. How long will it take the child to pull the train 3 meters? So we know the distance is 3.00 meters. And in the end, our unknown variable is the time. At this point, I recommend drawing a system diagram. Remember, a system diagram can show all the things happening in the system and can show forces acting on different things or applied to different things. So I first of all draw a reference coordinate system. I'm going to make up my positive y, and I'm going to make east my positive x. Now in my system diagram, I'm not required, bound by the same rules that a free body diagram has. So I draw the ground, I draw the 4 cars of the train, just as boxes. I'm going to number them, 1, 2, 3, and 4. At this point, I just add in the force of gravity on car 1, the force of gravity on car 2, the force of gravity on car 3, and finally the force of gravity on car 4. Now, we're on a level surface, we're on a surface making contact, so each of these will produce a normal force. So we have the normal force 4, normal force 3, normal force 2, and the normal force on car 1. Now, because we're on a level surface, these will all cancel out, so we do not have to worry about any y component in our forces, and the only thing we know, or to the system, is an applied force being given by a child who is pulling the cars. Now, this time, it's probably a good idea to look at a free body diagram. Well, in the question, it's specified that we know the force on car 3. Well, from car 2. 2 is not pulling 3, it's pulling 3 and 4. So I want to put them together like one car and then solve the question from that. So I'm now going to draw a free body diagram of car 3 and, or plus, car 4. So I'm going to make them into one box or represent them with one box. To do that, I know I'll need to put their masses together. So I'm going to call it m 3 plus 4, and I add 2.74 to 1.28, and I get 4.02 kilograms. Now I draw my free body diagram. So again, I represent cars 3 plus 4 as a box. I put the force of gravity. So remember, your free body diagram displays all of the forces acting on our thing, force of gravity. It is on a level surface. The normal force will cancel it out with the normal force of 3 plus 4. And then we have the force of 2 on 3. Friction was negligible, so we do not need to draw it. Now from this diagram, I could say, and remember we are still using the same reference coordinates we started with there, I could say the net force. So I'm just going to put a little separation, and I'm going to say the net force, net or total force on car 3 plus 4 will be equal to whatever force is applied to it plus the force of friction. Now, we're told in the question friction's negligible, so we don't need to worry about that. So we can rewrite it as F net 3 plus 4 equal to, and the force applied to it is F2 on 3. Now, using Newton's second law, I can take F net and change it to the mass, which would be mass 3 plus 4, times the acceleration. And F2 plus 2 on 3 I keep. Now, something I can take from this is, if this train is all joined, and we assume these couplings are massless and that they will not stretch or break, that whatever rate cars 3 and 4, car 3 is accelerating, the same as 4, 2, and 3, equals the acceleration of the whole train. And that's an assumption I need to make to solve this problem. So at this point, I can put in and fill in some numbers. 4.02 A. And I remember that I'm in kilograms with that. Now this F2 on 3 is Newton's east. So any direction I get will be in the east direction. I quickly divide 15 by 4.02, and I get 15 divided by 4.02. Remember, I will have newtons over kilograms. Well, that's the same thing. This is just a little dimensional analysis. Newtons over kilograms, which would be kilogram meters per second squared over kilograms. The kilograms cancel, leaving me in meters per second squared, which is the unit of acceleration. So that was a little dimensional analysis on the side. 15 divided by 4.02 is 3.73, keeping with our significant figures of 3 meters per second squared, and it will be in the east direction. Now that I have the acceleration, I know the initial velocity, or initial speed, I know the distance, and I know the change. I'm looking for the change in time. I can now go back and use a kinematics equation to solve this. So I'll roll this board out of the way, and I can set it up. I'm going to just rewrite some information. VI is 0 meters per second. Acceleration, I'm going to drop the vector now. They're looking for distance. We don't need to have vectors, so it's 3.73 meters per second squared. I know delta D as 3.0 meters. Now, VI and delta D were given in the question. I just used Newton's laws to solve for the acceleration. I check meters, 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 seconds, seconds. My units are all in agreement with each other. Whatever I solve for will be in time, or be in time, be in seconds, and I'm looking for time. So now I picked a valuable kinematics equation. For me, I like delta D equals VI delta T plus 1/2 A delta T squared. I fill in information. 3.00 equals 0 times delta T plus 1/2 3.73 delta T squared. And this will multiply to be 0. So I end up with 3 equal to 1/2 times 3.73 is 1.865. And it's never a bad idea to work with an extra digit past what you need for significant when solving a question, so I do that. I then will take 3.00 and divide it by 1.865, and that will be equal to t squared. After getting that, I get 1.609, again keeping that extra digit, t squared. So t will be equal to the square root. Just to get rid of a squared, I take the opposite sign of square root of 1.609. And I'll just come up here to finish it. So I get 1.27 seconds equal to delta t. And I could write a little statement. Therefore, it will take 1.27 seconds for the train to travel 3 meters.